everyone, in this video we're going to be learning about binomial probability distribution. So let's start by determining whether a probability experiment is considered a binomial experiment. So first we need to know what a binomial experiment is. So binomial probability distribution is a discrete probability distribution. So real quick, remember discrete, think of it as like counting numbers, that describes probabilities for experiments in which there are two mutually exclusive outcomes, or another way to say that is disjoint outcomes. So these two outcomes are generally referred to as success, such as making a free throw. If you were to shoot the basketball, the success would be making the shot, and then failure would be missing the shot. Experiments in which only two outcomes are possible are referred to as binomial experiments. And think of it as the prefix bi. Bi means two. So two outcomes, binomial. And this is provided that certain criteria are met. So criteria for a binomial probability experiment. Number one, the experiment is performed a fixed number of times. And each time we do the experiment, we call it a trial. Number two, the trials are independent. This means that the outcome of one trial will not affect the outcome of another trial. Number three, for each trial, there are two mutually exclusive or disjoint outcomes, success or failure. Number four, the probability of success is fixed for each trial of the experiment. Okay, so let the random variable x be the number of successes in n trials of a binomial experiment. Then x is called the binomial random variable. So some notation that's going to be used in binomial probability distribution. N represents the independent trials of the experiment. So if we do our trial 100 times, n would be 100. P denotes the probability of success. Okay, so if we wanted the failure probability, we would use the complement of p. That's why it's 1 minus p for the failure of each trial. And then x denotes the number of successes in n independent trials. So out of all the n trials, x is somewhere between 0 and n. 0 of the trials could be a success, 100 or however many n is can be a success, or anything in between. So first example, determine which of the following probability experiments qualify as a binomial experiment. So this is using our criteria that we discussed, the four things that need to be true. For those that are binomial experiments, so first we have to figure out if they are or not. Then we're going to identify the number of trials, the probability of success, the complement of that, which is the probability of failure, and then the possible values of our random variable. Okay, so first one, an experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of free throws made is recorded. Okay, so this is an example of a binomial experiment, and here's why. Number one, there's a fixed number of trials. There's 3. Each time the 3 shots makes up a trial. Number two, the trials are in fact independent. So one shooting of 3 times doesn't affect the next time this is repeated. Number 3, there are 2 possible outcomes, either make the shot or miss the shot. And then number 4, the probability of success, which is to make the shot, is 0.8 or 80%. And then the probability of failure or missing is the complement, so 1 minus 0.8, which is 0.2 or 20%. And the probabilities are the same for each trial. So each time this trial is repeated, the probability of making it is always 80%, the probability of missing is always 20. So the random variable x is the number of free throws made. So that could be the x would be 0 shots made, 1 shot made, 2, or up to 3. Okay, let's take a look at this one. According to a recent poll, 28% of Americans state that chocolate is their favorite flavor of ice cream. Suppose a simple random sample of size 10 is obtained and the number of Americans who choose chocolate as their favorite ice cream is recorded. So this is another example of a binomial experiment, and here's why. Number one, there are 10 trials, and that's the 10 randomly selected people, so a fixed number of trials. Number two, the trials are independent, they don't affect each other. Number three, there's two possible outcomes. Either the person chooses chocolate as their favorite or not. And then number four, the probability of success, which would be choosing chocolate as the favorite, would be 28%. And then the probability of failure, not choosing chocolate as the favorite, will be the complement, 1 minus 0.28, which is 0.72. And then our random variable represents the number of people who choose chocolate as their favorite, because remember, our binomial random variable represents the successes in this case. So the people that choose chocolate as their favorite could be anywhere from 0 to 10 of the people. How about this one? A probability experiment in which 3 cards are drawn from a deck without replacement, and the number of aces is recorded. This is not a binomial experiment because the trials are not independent. So the probability of an ace on the first trial is 4 out of 52 because in a 52 card standard deck there's 4 aces. So that's about 0.077 or 7.7%. But because we aren't replacing the cards, if an ace is selected in the first trial, the probability of an ace being selected again on the second trial changes from the first probability. That means there's only 3 aces left out of 51 cards because we didn't replace it. So that's about 5.9%. So if an ace is not selected on the first trial, the probability of an ace on the second trial is 4 out of the 51 remaining cards, which is 7.8%. So this is not an example of a binomial experiment because one trial affects another. Note that the word success does not necessarily imply something is positive. So I know it could be a little confusing, but just know that success refers to specifically as one of the two outcomes. Success and then failure is the other one. Success means that an outcome has occurred that corresponds with P, the probability of success. So on the chocolate flavored ice cream, just because we called choosing chocolate as your favorite a success doesn't really mean anything other than we knew the probability of it was P, or 80%. So next, let's compute probabilities of binomial experiments now that we know a little bit about what a binomial experiment is. According to the American Red Cross, 7% of people in the United States have blood type O negative. A simple random sample of size 4 is obtained, and the number of people X with blood type O negative is recorded. Construct a probability distribution for the random variable X. So quick reminder, a probability distribution means that we need to have the values for X, our random variable, as well as their probabilities. So step 1, construct a tree diagram listing the various outcomes of the experiment by listing each outcome as S, success, or F as failure. And then the tree diagram that we're about to look at has all of our possible outcomes. So first trial, we select a person and we say success if their blood type is O negative, failure if it's not. And then from there, the second trial, the second person could have the blood type O negative or not. Same thing down here, could have the blood type or not. And then we move on to the third trial, could have a success or failure. And then over here from the first one being a success, if the second one was a failure, the third one can be either a success or failure. So we just do this for each of the 4 trials, and it leads to these 16 outcomes. And so we have recorded over here the number of successes in each of the 16 outcomes. So only one of the 16 outcomes has 4 successes, and only one has 0 successes. And then notice we do have some different ones where we have 3 successes, 2 successes, and 1 success. So now compute the probability for each possible value of our random variable. So remember, the random variable is representing the successes. So the probability of 0, okay, that only happened once, and so it's the probability of failure, 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 which our multiplication rule that we learned in the past, the way you can compute this is just multiplying the individual probabilities. And so for us, that's 0.93 or 93% for each of these failures. And just real quick, why this is 0.93, if you remember, we were told that a person having blood type O negative, the probability was 7%. So this is the complement of that. 1 minus 0.07 is 0.93. And so this is just repeated, so you can just use an exponent to get 0.74805. Now we move on to the probability of one success. This can happen 4 different ways. So the success could be done in the first trial, second trial, third, or fourth. And so our addition rule that we learned before for disjoint events, we add our individual probabilities here of the 4 possibilities. And then now we kind of combine 2 things here, our addition rule with our multiplication rule. So let's talk about this real quick. So just within this first trial, let's say, the first person, it was success, the next 3 were failures. So there was 1, so it's this thing up here, but just sort of expanded down here. So 1 for success, so that percent was 0.07, and then that's why it's a first power. And then the other 3 would get multiplied, just like they did up here. We could just say 0.93 is the third power. And so same thing over here. Every time we have 1 of our probabilities for success times 3 of the probabilities for failure. We do that again and again. So for each of these 4 outcomes here. And then just to have our notation, you don't really have to do this, but notice it's 4 of the same thing, 4 of the same term. So you could just say 4 times this product. And we do all that and we get 0.22522. Now let's compute for 2. So probability of 2 successes. So this can happen 6 different ways. Success, success, failure, failure, success, failure, success, failure, and so on. And so we have to see what happens with each of these. And so for each one here, it's actually going to be the same setup. 2 of them were successes, so 0.07, and then we can multiply that twice, or say to the second power, times 2 failures, so 0.93 times itself, or to the second power. And this happens 6 different times, and so we could just say 6 times that product, and we get 0.02543. And then we do the same thing for probability of 3 or 4 successes, and we would get these outcomes. So we would get the probability of 3 successes is 0.00128, and probability of 4 successes is 0.00002. And so notice the number is actually pretty small for the probability of 4 successes compared to some of our other numbers. And so we're going to represent these results in our probability distribution table. So we talked about this, but remember, for it to be called a probability distribution, it has to have the values of your random variable also listed with their probabilities. All right, so the binomial probability distribution function. Okay, so this is a new kind of formula that we're going to learn. The probability of obtaining x successes in n independent trials. So we're doing a trial n times, and x is the number of successes. As if the experiment is binomial, then this probability is found using this calculation right here. So what this says, and we've seen some of this in the past, probability of x equals, this was our combination formula from the past. So n, choose x, we had a formula for that. You can also use a calculator for that, but this is combination, n combination x, times, so there's an invisible multiply sign here, times your probability raised to the x power, and then times that by the complement, or 1 minus the probability, and then that's being raised to the n minus x power. Okay, and x has to go from all values from 0 to whatever n is. Okay, so this formula, again, gives you the probability of getting x successes out of your n trials. So if we wanted probability of 2 successes, like from our previous example, everywhere we had an x, we would put a 2, and then out of our trials, n would be replaced with how many trials we did. So when reading probability problems, pay special attention to key phrases that translate into math symbols. So a lot of times with math, we have to take the words and we have to translate them into some kind of math symbol. And so here's just a few of our equivalent English phrases with math symbols. At least, no less than, or greater than or equal to is all this inequality symbol here with the bar underneath, okay? Because it can equal the number as well. More than or greater than, same inequality symbol, but no bar underneath. Fewer than or less than is just facing the other direction. And then no more than, at most, less than or equal to is our same inequality symbol facing the other way with a bar underneath. And then exactly, equal, or the word is an equal sign. So let's try this out. According to CTIA, 72% of all adult Americans would rather give up chocolate than their cell phone. In a random sample of 10 adult Americans, what is the probability that A, exactly 8, would rather give up chocolate? Okay. So the nice thing is we don't have to do necessarily anything by hand. We can just plug into our binomial formula here. So we have probability of 8 successes. So remember here, in this case, give up chocolate, in this case, rather than cell phone, give up chocolate would be success. So exactly 8 would give up chocolate. That's probability of 8. So we had 10 in our sample, so n is 10. Choose 8. The probability of success is 0.72 raised to the x power, in this case that's 8. Then we times that by the complement of our probability, so 1 minus 0.72, and then n minus x, or in this case 10 minus 8. And then if we start simplifying, if you remember when we learned about combinations, this was the formula. It was n factorial over 8 factorial times 10 minus 8 factorial. So real quick with letters, if you recall, it was n factorial over r factorial times n minus r factorial. And then notice we just simplified the exponent here. It was 2, and we simplified inside the parentheses, that's 0.28. And then we just calculate, you can use your calculator for this, 25.48%. So let me just write that formula out real quick. So n factorial over r factorial, excuse my handwriting, I'm using the mouse, times n minus r factorial. And this was your combination formula for n, choose r. So that's equal to this formula. That's where this came from right here. Okay, so let's interpret what we just learned about. The probability of getting exactly 8 adult Americans out of 10 who would rather give up chocolate is about 25%. In 100 trials of the study, that means if we surveyed 10 adults 100 different times, we would expect about 25 of the trials to result in 8 adults who would rather give up chocolate than their cell phone. So just a way of interpreting the value that we got. Now let's compute the number of probability that fewer than 3 would rather give up chocolate. So let's translate fewer than. Fewer than is the same as less than. So the values can be anything less than 3 of our random variable, which is 0, 1, or 2. And so you can write it like this: probability that x, our random variable, is less than 3, but then you want to expand that for the values that it can assume, which is 0 or 1 or 2. And then we know that we can add up those individual probabilities. So probability of 0 plus probability of 1 plus probability of 2. And so what we have to do in the next step is we have to actually compute these probabilities using our formula for binomial probability 3 different times. So notice we have our formula right here when x is 0, n is still 10. And then we have our formula right here when x is 1, n is still 10. And then right here, our formula for when x is 2 and n is 10. We would simplify each of the parts of the terms, and then we would end up with, after we get all those and add them up, 0.00096, or about 0.96%. 0.096%. So to interpret that, the probability that in a random sample of 100 adults, fewer than 3 would rather give, 10 adults, fewer than 3 would rather give up chocolate than their cell phone is about 0.00096. So that means in 1,000 trials of this study, we would expect about 1 trial to result in fewer than 3 Americans who would rather give up chocolate. So the 1 came from rounding. This 96 here, if you round to the thousandths place, you can round that up to like 10 or 1 in the thousandths position. So that's where 1 out of 1,000 came from. Now let's compute the probability that at least 3 would rather give up chocolate. So this is kind of the opposite of what we just did. The values of the random variable that are at least 3, at least includes the number you're talking about. So at least 3 includes 3, and anything greater than 3. So it can be anything 3 to 10. So we could compute probability x is greater than or equal to 3 by doing exactly what we just did, but it's going to be a little longer because we have to do probability of 3 plus probability of 4 and so on all the way up to 10. So it's going to be our binomial formula quite a few times. But because we've already done the opposite of this, we're going to go ahead and use the complement rule. So anytime you can use a complement rule, you should, because it saves time. And so the probability that x is greater than or equal to 3 is the complement of probability of x is less than 3. So you could say that this probability equals 1 minus the probability of the complement. That's how complements work. Remember how that goes. Probability of a success and it is equal to 1 minus probability of failure, or vice versa. And so we already did all that work to get the probability that x was less than 3. So the fastest way to get probability of x is greater than or equal to 3 is just do 1 minus that answer. So that would be 0.9990, or about 99.9%. So the probability that in a random sample of 10 adult Americans, at least 3 would rather give up chocolate than their cell phone is about 99%. So in 1,000 trials, we would expect 999 of them to result in at least 3 stating they would rather give up chocolate. Okay, now let's compute the number of adult Americans who would rather give up chocolate. That's between 5 and 7, including 5 and 7. Okay. So inclusive just means including. And so we want to determine the probability that we have 5, 6, or 7 people that would give up chocolate. Okay, so the way we can write this, a little typo here. This should have an equal bar. Okay, so probability that x is greater than or equal to 5 or less than or equal to 7. And so that's the same as the individual probabilities of 5 plus probability of 6 plus the probability of 7. So we do have to use our binomial formula 3 times here, where in the first one, n is 10, x is 5. In the second one, n is still 10, but x is 6. And in the third one, x is 7. And then we calculate those, add them up, and we get about 52.79%. And so the probability that the number of Americans who would rather give up chocolate that between 5 and 7 inclusive is about 52.79%. So another way to say that, in 100 trials of this study, we would expect about 53 of the trials to result in 5 to 7 adults who would rather give up chocolate than their cell phone. All right, let's try a different example. No more chocolate and cell phones. According to a Gallup organization, 65% of adult Americans are in favor of the death penalty for individuals convicted of murder. In a random sample of 15 adult Americans, what is the probability that A, exactly 10 favor the death penalty? So in this case, N is a 15, okay, because that's our sample size. The probability is 65% or 0.65. And then we're looking for exactly 10 to favor this. So X is 10. So we're going to look at a table here in our appendix and go to the section that contains N equals 15, the column that has a corresponding probability, and then the row for X equals 10. And so what this table is it's actually the computations, so you don't have to do this probability, binomial probability calculation by hand. Okay, so here's our table, and you can find this table in a lot of places, but we have a snippet of it here. So we go down, we find when N is 15, and then we go to probability of 0.65, and we say, where does that meet with X equals 10? And so where those meet is right here, and so we get 0.2123. So in stats, a lot of times there's tables of values that you can find online or reference in books, and so you don't have to perform all these calculations all the time, especially for binomial probabilities. So this is a binomial table. So a way to interpret this result, in 100 trials of this study, randomly selecting 15 adults, we can expect about 21 of the trials to result in exactly 10 adults who favored the death penalty for individuals convicted of murder. And that 21 came from right here, the 0.2123. Okay, so now let's compute the probability that no more than 6 favor the death penalty. So no more than is the same as less than or equal to. Okay, no more than 6 means 6 or less. So to compute the probability that X is less than or equal to 6, we're going to use a cumulative binomial table. It's a different table. It's cumulative because we want all the probabilities that are 6 or less. So instead of computing probability of 0, probability of 1, probability of 2, all the way up to 6, we have a table that already has that computed for us for the cumulative binomial probabilities in this case. So this lists binomial probabilities less than or equal to specified values. So in our case, N is still 15, P is still 0.65, but now we're going to look for the row corresponding to X equals 6. Okay, and so this is a different table. So this would be the table for cumulative binomial probability distribution. So again, you can find these tables normally in a textbook or online. Okay, so now we're going to do the same thing, but we're going to use technology. So I'm going to show you how to compute these probabilities, one for exactly for X equals a number, and then one for no more than, so the less than or equal to. We're going to use StatCrunch and then the TI-84 calculator. Okay, so for our binomial distribution, we're going to go to Stat, Calculators, Binomial. And this is really nice because it just lets us type in things quickly. So let me clear what was there. And we had N was 15. Our probability P was 0.65. And the first one we wanted was the probability of X is exactly equal to 10. And we hit compute. And here's our graph for us. And then we have our value, 0.2123 approximately, which is the same value we got from our binomial table, our binomial distribution table. So let's change this, and now let's do X is no greater than 6 or less than or equal to 6. So new graph, new probability, 0.04219. And then that's what we had gotten from our table, our cumulative binomial table. And just to show you in case you need to, If you needed the probability between two values, you can hit between right here, and then you can change the lower value and the upper value. And so that's also possible. So now let's do this on a calculator. Okay, so what I'm going to do here is I'm going to go to distribution, which is a background here in blue. So I'm going to hit second, vars. That's my distribution. Now I'm going to go the slow way to show you. It is going to be down here on the list. So we have all these options, and we're going to get a little further, and it's right here. Letter A is our binomial probability distribution function. So binom PDF. So that's the first one we want. That one's if it's just for an exact value for x. We're also going to use binomial cumulative distribution function if we want something either less than or greater than some number. So for the first part, for x equals 10, we're going to use binomial probability distribution function. So I'm going to hit enter. And real quick, I want you to remember the next one we need is labeled letter B. So I'm going to show you a shortcut for how to get there. So for now, I want this one. And we had 15 trials. Our probability was 0.65. We want when x is 10, and we're going to go down to paste, and then it's going to use our binomial probability distribution function formula, enter, and there's our calculation. So 0.2123. Okay, so now let's do x is less than or equal to 6. So second distribution. This time, the shortcut is it was labeled B. So if you look in green here, B is labeled in green right here under apps. So I'm going to hit alpha, apps. That activates the green. So it took me right to binomial cumulative distribution function. So I didn't have to use the arrow to go down there. So 15 trials, 0.65 for the probability. This time we want x is less than or equal to 6. So we just put 6. And we paste that. And because we're using the cumulative function, it's going to go ahead and do everything less than or equal to 6. So that's 0.0421. Okay, so that's our same calculations using technology. Now let's compute the mean and standard deviation of a binomial random variable. So the mean, or the expected value, and standard deviation of a binomial random variable can be found with the following formulas. So remember, n represents the number of independent trials, p is the probability of success, and then our standard deviation is denoted with sigma. So remember, mu sub x is the mean of our random variable. That's a notation for it. And the calculation is just n times p. And then the standard deviation of our random variable, sigma sub x, is square root of n times p, and then you multiply that times 1 minus p, or the complement of p. So pretty simplified formulas for the mean and the standard deviation when it comes to the binomial random variable, as opposed to other formulas we've seen in the past for mean and standard deviation. So take a look at this example. According to CTIA, 72% of adult Americans would rather give up chocolate than their cell phones. We've seen this earlier. And so a simple random sample of 300 households determined the mean and the standard deviation and of a number who would rather give up chocolate than their cell phone. So out of 300 households. So the mean is just going to be n, which is 300 in this case, times the probability p, which is 0.72. And so mu sub x, or our mean, is 216. Our standard deviation is going to be n, which is 300, times p, 0.72, and then the complement of p, which is just 1 minus 0.72. Do the subtraction first, and then multiply all three of these values, take their square root, and you get 7.8. And so we can interpret this and say we expect that in a random sample of 300 adult Americans, 216 would rather give up chocolate than their cell phone. So now let's graph a binomial probability distribution. And so we're going to graph the binomial probability distribution for n equals 10, probability is 20% or 0.2, and then comment on the shape of the distribution. Okay, so I'm in StatCrunch here, And I've already created my probability distribution table. You can get these probabilities here by using your formula, your binomial distribution function by hand. But let's go ahead and use technology. So I'm going to go stat, calculators, binomial. And for us, n was 10. We were told the probability is 0.2. And I'm going to go ahead and just do this for each of my outcomes that I want. So probability that x is 0. I get 0.1073 roughly, rounded to 0.74, and that's how I got this value for the probability of 0. I can do that again for the probability that x is 1, and I got 0.2684, which is how I got this number here. You can do that for all of them, and then notice if I do the probability of 10, it's not actually 0, but if we round to 4 significant digits, it is looking like 0, but it's technically not exactly 0, just very close to 0. So that's our probability distribution table. That's how we got it from just knowing n and p. Once I already had this table here, if I already had these values, I can go to stat, calculators, custom, and I could say my variables in var 1, my weights are in var 2, and there's my graph. Okay, and so notice what we have here. We have the mean given, standard deviation given. We've seen this, we did this earlier. And so what we want to look at is what can this graph tell us? What are we seeing here with this graph? And so let's go ahead and go back to our slides and talk about it. Okay, so just real quick, here's our probability distribution table that we figured out in StatCrunch. Another way you could do it is to use your binomial distribution table that you can find online or in your textbook. And that's how you can get these values as well. You don't have to use the technology, you can just use your table to fill these values in. And so our graph, if you notice, it looks like our distribution is skewed right. Remember, skewed right looks like the tail is longer toward the right. So this data is skewed right. Okay, so now let's do another one. Graph the binomial probability distribution. N is still 10, but this time the probability of success is 0.5, 50%. And then comment on the shape of the distribution. So you can create your probability distribution table the same way we did in StatCrunch. You can use your table, you can do it by hand, or you can use a calculator, lots of different ways, and you will get this probability distribution table, and then we can graph it, and we get this nice symmetric distribution. Okay, so it's approximately bell-shaped. Remember that? The bell-shaped looks like this symmetry is going on. And now one more. N is 10, probability is 80% or 0.8, and using any means we prefer to get our distribution table here. Then our graph looks like the following, and notice this is skewed left because the tail of the data here, their probability is longer toward the left. And so we've seen the role that the probability P plays in the shape of a binomial distribution, but what role does N, the number of trials, play in its shape? So the figure shows the graph of 3 binomial probability distributions found using StatCrunch. In this first figure, N is 10, P is 2. This is actually the one we did. The second one, N is 30, P is 0.02. Oh, sorry, that was 0.02, 20%. And then the last one here, N is 70, and P is 0.2. So all of these have the same probability of 20%, but N is increasing as we go from graph 1 to graph 2 to graph 3 here. And look at what it's doing to the shape. The first one was skewed right. The second one is still kind of skewed right, but notice this curve is kind of pushing its way toward the middle here. And then the third one, it's much more symmetric or bell-shaped. And so, like I said, it's skewed right, slightly skewed right here as N increased, but as N got bigger and bigger, it looks more bell-shaped. And so for a fixed probability, or P, as the number of trials N in a binomial experiment increases, so if you keep doing this trial over and over, and increasing that number, the probability distribution of the random variable x becomes bell-shaped. And so a rule for us is that if n times p times 1 minus p, so the number of trials times the probability of success times the probability of failure. If that's greater than or equal to 10, the probability distribution will approximately be bell-shaped. So this is a nice fact for binomial probability distribution. So according to CTIA, 72% of adult Americans would rather give up chocolate than their cell phones. And so in a simple random sample of 300 adults, 230 indicated they would rather give up chocolate than their cell phone. Is this result unusual? So from our previous example, we figured out that the mean, mu, was 216 and that the standard deviation, sigma, was 7.8. And so look what we're calculating here. Notice what this is interpreting as. The mean minus 2 standard deviations, we'll plug in our numbers for the mean and standard deviations, equals 200.4. The mean plus 2 standard deviations is 231.6. Okay, so this is saying, remember the mean's like the middle, the average almost. Not quite the middle, that would be the median, but think of it like the common middle value. That's a good way to remember. And so this is saying within 2 standard deviations less than the mean, within 2 standard deviations greater than the mean. Okay? And so since any value less than 200.4 or greater than 231.6 is unusual, this number of 230, it's in between these two, and so it's not unusual. It's within 2 standard deviations, either above or below the mean, and we don't consider that unusual or an outlier. And if that's sounding familiar, it's because we learned previously when we have bell-shaped distribution, we had the empirical rule that said 95% of our data was within 2 standard deviations of the mean. And so 95% of the data is within 2 standard deviations. And so because this number was within 2 standard deviations of the mean, it's not unusual. All right, that's it for this one, everyone. Thanks for watching.